Thank you very much for introduction, and I'm very glad that I have the opportunity to share my recent research work in this SPICE workshop, Coherent Order and Transport in Spin-Active Systems. I'm Tomosato HIOKI from the University of Tokyo and Tokyo University. And firstly, I'd like to thank all the collaborators and my group leader, the Professor Eiji Saito, and also the collaborators in Tokyo University and the University of Oslo. And this work is funded by the JST Ratos and JSPS research fundings. So let me show my outline of the presentation. I'd like to talk about the Magnon-phonon, the dynamics of the Magnon-phonon hybridized waves. And I'd like to begin with the introduction of the Magnon-phonon hybridization. So the spintronics has been developing, involving a lot of interconversion phenomena regarding the electric current, or spin current, or even heat current. But the spin current is one of the key concepts in spintronics. That is the pure spin angular momentum transfer in the magnetic materials, including the various different materials. And especially as presented by the previous talk, in the magnetic insulator systems, the spin current is mediated by the magnons, the quanta of spin waves. The spin wave is the collective precessional motion of the magnetic moments propagating as a wave in the magnetic materials. And it can be controllable by the magnetic field, external magnetic fields, or some microstructuring. And ultimately, the spin current transferred by the magnons are relaxed to the systems because that's why they have a certain decay length or the propagation length. And ultimately, the magnon goes to relax to the phonon systems and loses the spin angular momentum transfer. And phonon, a quanta of elastic wave, has the two different modes, transverse and longitudinal modes. And normally, for example, in the IG, which is the typical material for the spintronics, insulator spintronics, the phonon has a much longer coherent and propagation length compared with the magnons. And however, this phonon, the role of the phonon is limited just as a kind of ultimate relaxation channel for the magnons in the previous spintronics fields. But when we look at the wave nature of these excitations, the story becomes a little bit different. So I show the so-called dispersion relation, the energy momentum relation of the magnons and phonons respectively. And owing to the dipole type interactions in the long wavelength regimes, the magnons has a very flat band structures, while the phonon has a zero gap and has a linear dispersion relations. And therefore, they have the two crossing points in the spectrum space where the Magnon-phonon hybridized wave can be a new normal state at the crossing points because they have exactly the same wave number and frequency. So since this Magnon-phonon hybridized waves inherits a property of the both magnons and phonons, and therefore they can transport the spin angular momentum much longer distances. And that is appearing even also in the spin transport measurement by using the spin-Zwick effect. And also there are some spectroscopic studies to observe the Magnon-phonon hybridized waves in the spectrum space by the VLSI scatterings. So recently, the Magnon-phonon hybridized waves can be the candidate for the spin transport. However, there are limited access to the investigation on the propagation dynamics of this hybridized wave. And that's what we want to investigate. That's what we want to elaborate in this presentation. So in order to realize the observation of the dynamics of the Magnon-phonon hybridized waves, we recently developed the time-resolved magneto-optical imaging technique so that we can take the snapshots of the propagating Magnon-phonon hybridized waves in the real space as shown here. So I'd like to explain some recent results by using this time-resolved magneto-optical imaging technique involving the bireflection of the spin waves and the coherent oscillation between magnons and phonons. So let me go on to the bireflection of spin waves first. So, so I would like to elaborate the time-resolved magneto-optical imaging first. So here is the movie of a typical movie that we can obtain from the time-resolved magneto-optical imaging technique. This is the combination technique that uses the conventional magneto-optical imaging and the pump and probe spectroscopy. So by using the femtosecond pulse laser, we can realize a very nice time resolutions within the picoseconds, and we can take this kind of movie of the propagating spin waves or the hybridized waves. The excitation of the magnetization dynamics can be performed by using so-called pulse laser, the femtosecond pulse laser, which incidents to the sample. And this laser heats up the sample very locally on the focus positions. And this creates the thermal expansion and leads to the phonon excitation and also the magnon excitation by demagnetizations. And observation of the magnon propagation can be performed by measuring the angle of rotation of the transmit light or the ellipticity of the transmit lights. So depending on the magnetization configuration of the sample, we can use either Faraday effect or the Cotton-Newton effect to visualize the real space propagation dynamics of the magnons or the Magnon-phonon hybridized waves. Here I showed example that we input the spin waves into the 90-degree domain wall, and it refracts in a negative with negative refraction indexes. This kind of dynamics can be observed with using the time-resolved magneto-optical image. So here I would like to go on to one of the main topic, the bireflection of spin waves. So when we consider the reflection of the magnons, it is we can use the analogy to the light. So when the magnon is incident to the sample edge, for example, then what we will see is a single magnon ray reflected back with forming the same reflection angle as the incident angles. This is simply because when the magnetization is perpendicular to the film, the spin wave dispersion relation is isotropic, and also it's almost a single mode, and therefore the reflected beam should form the same angle with the incident angles. This is simply analogous to the light reflection. However, the situation becomes slightly different when it comes to phonons case. When we input the longitudinal mode of phonons, for example, at the sample edge, what we will see is the two different reflections. One is ordinary reflection, and the another is the extraordinary reflection. This is because the phonon has two different modes, and therefore the reflection mode can be split into two. One is the longitudinal, and another is the transverse modes. Therefore, this leads to the extraordinary reflection in addition to the normal reflection. So the question arises what happens if we incident the hybridized Magnon-phonon hybridized waves into the sample edge? Naively thinking, what we can expect to see is the splitting behavior of the reflected wave because the phonon should split. However, if this is realized, it is very unconventional behavior for the magnon case because the magnon ray should be 1. So that's what we want to experimentally investigate. So we use the bismuth-doped iron garnet film to measure the dynamics of the hybridized waves. This material is preferable for our measurement because they have large Faraday rotation, large magneto-optical activity, and also the small magnetization and small anisotropy. And we change the focus shape so that we can control the propagation orientation of the excited Magnon-phonon hybridized wave towards left top orientation in this picture and guide it to the sample edge cleaved mechanically and observe the reflection dynamics of the Magnon-phonon hybridized waves in the vicinity of the sample edge by using the Faraday effect. So here I show one of the main results. So this is the picture taken after 12 and 18 and 24 nanoseconds after the pump beam irradiation. And right after the pump beam irradiation, you can see that the wave of a Magnon-phonon hybridized wave is propagating towards left top orientation, and it reflects back and split into two different waves with a different wavelength. Since these data are obtained with the two-dimensional spatial axis and one-dimensional time axis, we can reconstruct the Fourier spectrum, the spectrum of the excited waves by performing a 3D Fourier transform. And what we can see is the intensity is greater in the region where the spin wave dispersion and the longitudinal phonon dispersion has a crossing. So when we cut the spectrum at a certain frequency plane, then what we can obtain is the wave number space spectrum. We perform this analysis before and after the reflection, And what we can see is a clear splitting behavior of the reflected waves. So before the reflection, there is a single mode appearing in the spectrum space, indicating the single mode propagating towards the edge of the sample. And while after the reflections, they split into two different waves with conserving the y component of the wave numbers. This is typical behavior for the splitting behavior for the phonons, longitudinal phonons. And also we checked that this splitting behavior follows to the Snell's law of the phonon splitting behaviors. Since we can simply calculate the Snell's law by considering the dispersion relation of the phonons, longitudinal modes and transverse modes, and experimentally observed result is following. It just follows to what we expect from the phonons reflections. So the question arises if this is really the dynamics of the hybridized waves or not. Just right? Is it just phonon dynamics observed through the magnon-phonon, magneto-optical effects? To answer this question, I have two different data. So the first one is the confirmation of the hybridizations. So we can calculate the phase velocity and group velocity out of these magneto-optical images by using the magneto-optical image and also the transformed data out of this magneto-optical images. And the magneto-optical image just gives us the phase velocity because it just reflects the phase. And when we perform the Hilbert transform to this data, we can get the envelope group velocity. And what we can get as a result of this analysis is that we can see that the phase velocity is a little bit larger than the group velocity within the error bar, which means that the excited wave is indeed the mixture or the hybrid, the combination between the magnons and phonons, where the group and phase velocity should be the same for the pure phonons case, which has the linear dispersion relations. And also, I have modeled the reflection behavior by using the three different scattering procedures to calculate the incident angle dependence of the reflectivity of the hybridized waves. So we consider the simple spin wave reflection process and elastic reflection process, and also the elastic mode conversion processes. And by putting these processes to the phenomenological scattering Hamiltonian, we can calculate the incident angle dependence of the reflectivity of each mode. So here I show the results. So the blue and red circle points are the experimentally obtained reflectivity of the two modes, reflected two waves. And you can see that this black dashed line shows the pure phonons case for the reflectivity, incident angle dependence of the reflectivity, and it does not fit to the experimental result. However, when we consider the hybridization into account, then what we can obtain as a reflectivity is this solid blue and red curves, which fits very well to the experimental results. So that's why we conclude that what we are observing is the dynamics of the hybridized waves. So let me summarize the first part. So we tried to observe the unconventional behavior of the magnetization dynamics owing to the hybridization between magnons and phonons. And we observe the bireflection behavior of the magnons owing to the mode degree of freedom of phonons. And let me go on to the next part. The first one, the next part one is the coherent oscillation between magnons and phonons. So I just used the term Magnon-phonon interaction in the previous slides, but it can be categorized into roughly two contributions. One is the magneto-elastic coupling, the lowest order interaction between magnons and phonons. And another one is the Magnon-phonon scattering, which originates from much higher terms of the much higher order interactions. So for the lowest order interaction, they lead to the formation of the hybridized waves, as I mentioned before, and which in the spectrum space, it gives you these types of the avoided crossing structure, and the coupled mode has the two different frequencies. However, when the Magnon-phonon scattering becomes dominant, it leads to the broadening of the dispersion relations owing to the Magnon annihilation process or the Cherenkov processes. So when the broadening of the dispersion relation is large, what we see is we cannot really distinguish these two Magnon-phonon hybridized wave modes very clearly. So what and there are the temporal dynamics of these types of the the temporal dynamics is a kind of indicator for distinguish these two different situations. For when the magnetoelastic coupling is dominant and two modes can be distinguished, then what we would see when we look at only the magnon or either the magnon or the phonon parts only is that the coherent oscillation of the amplitude of the magnons. For example, when in this case when we look at the magnon amplitude only, what we will see is the oscillation of the magnon amplitude becomes like this way. So when the magnon is excited, it goes to phonons at a certain time, and it goes back to the magnons at a certain time. And this oscillation frequency is determined by the gap between these two states. And while the Magnon-phonon scattering is dominant, when the Magnon-phonon scattering is dominant, we will see the damped oscillations. So there is a discussion on in which states the magnons in the magnetic current are. So we would like to investigate this in an experimental way. So we extend the time-resolved magneto-optical imaging technique by using optical fibers so that we can access to the very high frequency resolution of the 28 megahertz, which is enough to observe the gap owing to the Magnon-phonon hybridizations. So we shape the pump beam into a line shape so that we can excite a plane wave of the hybridized waves propagating parallel to the external magnetic fields. And what we can see as a result is just like this. So we can see the plane wave propagation towards left to right. And as we did in the last topic, we can perform the Fourier transform so that we can to reconstruct the spectrum. And what we can see is here. So the intensity is strong at the crossing point between the magnon dispersion and the phonon dispersions. However, when we look at on top of that, when we look at closely to the crossing point between magnons and transverse phonons, what we can see is the discontinuity of the dispersion relations and leads to the two different peaks at a certain wave number. It means that we have the magnetoelastic coupling dominant situation in these materials. And in this case, where the magnetization and in this case, we should see the coherent oscillation between magnons and phonons. So in this configuration, where the magnetization and Wavevector are parallel to each other, then what we would expect from the symmetry of the magnetoelastic coupling is that strong coupling in the transverse mode and small coupling in longitudinal modes, leading to the coherent oscillation to the transverse modes and no oscillation to the longitudinal modes. And we extract the time evolution of the spectrum intensity by performing only the spatial Fourier transformation for each frame and reconstruct the temporal evolution of the spectrum intensity. And what we can see is shown here. So the upper panel shows the temporal evolution of the magnon amplitude in at the crossing point between the transverse phonons, while this shows the crossing with the longitudinal modes. And obviously, for the transverse mode, they have the magnon have beating behaviors, having one node and two antinodes, while the longitudinal mode does not show anything, meaning that there is a very weak interaction between magnons and phonons for the longitudinal modes. So we can model that behaviors by using the coherent state defined by the diagonalized Hamiltonian of the interaction of the Magnon-phonon hybridized systems. And we can calculate the mean magnon number at arbitrary time t, which shows the time dependence of the cosine-like oscillation behaviors. And this delta f is the difference between the upper branch and lower branch. And this delta f should have a clear linear dependence on the wave numbers, and we experimentally confirm that. So we perform the different measurement at the different magnetic fields and measure the oscillation frequency at the different wave numbers. Then what we could see is the very well correspondence between the experimental result and calculations for different magnetic fields. So that's why we conclude that what we are observing is the coherent oscillation or the interconversion between magnons and phonons. So to sum up my presentations, I'd like to show some data here again. And we developed time-resolved magneto-optical imaging techniques so that we can obtain the propagation dynamics of the Magnon-phonon hybridized waves. And as a result, we could see the bireflection of the spin waves, the magnons, as a result of the more degree of freedom of phonons, and also the coherent oscillation between magnons and phonons, and coherent interconversion between magnons and phonons. So thank you very much for your listening.